Good afternoon. I'm Cheryl Warner in NASA's Office of Communications. Welcome to What's on Board, where we highlight some of the cool science that we're sending to the International Space Station. Our next cargo delivery will be SpaceX's 8th cargo resupply mission to the space station. A Dragon, which will launch atop a Falcon 9 rocket, has been loaded with 7,000 pounds of science research, technology demonstrations, and supplies for our crew aboard the orbiting laboratory. The target launch date for SpaceX CRS-8 mission is Friday, April 8th at 4:43 p.m. Eastern from Cape Canaveral Air Force Station in Florida. NASA television coverage begins at 3:30 p.m. We have a fantastic lineup of speakers for you all today. We will discuss a student-designed DNA investigation, demonstration of an expandable habitat, and other research that will inform NASA's journey to Mars. After each speaker, we will have an opportunity for question and answer. We'll start with questions in the room. If you have a question, please raise your hand. If you're listening on the phone line, please press *1 at any time to enter the queue. And if you're watching us online, please use the hashtag AskNASA. Now, our first guest is Joya Massa. She is the science team lead for Veggie 03 right here at Kennedy Space Center in Florida. Joya, can you please explain to us how growing vegetables aboard the space station will help further our deep space exploration goals?
Thank you, Cheryl. So Veggie 3 is our latest experiment that will be going in the Veggie hardware on space station. And for Veggie 3, we're actually going to be testing. For Veggie 3, we're actually going to be testing a new crop in the Veggie hardware that will be a small Chinese cabbage called Tokyo Bacana Chinese cabbage. And this, along with our other veggie testing, gives us a lot more information on how we can grow crops to provide supplemental nutrition to the astronauts as we start to do, regular salad crop production on space station in the near future, and then possibly even more types of foods as we go towards our journey to Mars. So our Chinese cabbage variety was selected because we did tests of a number of leafy vegetables looking specifically at how well the plants grow, their nutrient content, and their organoleptic or taste components. We actually grew additional crops, sent them to Johnson Space Center, where in the food lab they did taste test evaluation. This variety was both the best growing and the most highly acceptable flavor of all of the crops tested. So we chose to send this variety with this mission, as well as some additional seeds of the red romaine lettuce that we've grown before in Veggie. This time with Veggie 03, we're going to be testing autonomous gardening, so having the crew garden in response to the plant's growth without, specific directions from the ground team at every step of the way. And we'll see how the Veggie system works with this new approach. So we'll show you a few photos of the processing and preparation of what we call our plant pillows. So if we could have the first photo. This is our Veggie team, and what we're doing is we're weighing or measuring out the media, the substrate that goes inside the pillows, which is a baked ceramic clay. It also has controlled release polymer fertilizer mixed in there. If we go to the second photo, you'll see testing of the plant pillow itself, looking to make sure that air penetrates through all the tubing in there. We want to make sure everything is performing flawlessly. If we go to the third photo, you can see the filling of the plant pillow. So we insert the precisely measured volumes of media into these plant pillows, and these pillows are essentially our space grow bags. So they interface with the Veggie hardware that's on space station. Everything is sent up dry, and the astronauts will add water when they get there. So if we go to the next photo, you'll see that the pillows then get sewn shut here, and this is all done in our laboratories at Kennedy Space Center. And the following photo will show you a kind of a close-up of that sewing process. And then the next thing that happens is shown in the next photo. This is our seed planting. So we have these wicks that penetrate through the media, and this is what kind of establishes a water column. And the seeds are inserted in these wicks. These are sterilized, surface sterilized seeds. So everything we send up is clean. All of these activities are done under very clean conditions so that we're not introducing any contaminants. And so you can see here a shot of seeds being inserted, and they're glued in there with a weak glue to keep them in place for launch. And then when the astronauts add water, the seeds will hydrate. And I think we have one more photo of pillow preparation. You can see the pillows are then sealed up in gas impermeable bags because we're not entirely sure when these plants will be grown. And so some of them may be grown, several months from now. So we want them to be just as fresh as the day that we packed them. So we seal them up. This photo was also going on this week. So in the midst of all our preparation for planting for this flight, I had an opportunity to represent the Veggie team at the First Lady's Garden in Washington, D.C., where we planted the same crops that we're sending up on this SpaceX mission. So you can see there in the foreground, the red romaine lettuce, and just behind it, the Tokyo Bacana Chinese cabbage. So those are growing in the White House kitchen garden right now, where, the White House will be eating the same plants that the space station astronauts will get to eat. So that's Veggie 3 in a nutshell.
Thank you, Joya. We'll now go to questions, and we'll start with questions from the room, please. Right here.
Yes, can you tell me, looking at the future in space, Chinese cabbage at the current present time, if you were to look at astronauts and, let's say, carbohydrates, trying to get the most value out of the vegetable grown in terms of the most it could produce in the amount of food, would you be looking at, let's say, potatoes, other type crops that are going to produce more in the way of carbohydrates? Also, would we be looking at the future where before the Mars would be landed on, that possibly you could be looking at a greenhouse operation tested on the surface of the moon? And if so, would we be looking at the values of the sun in terms of what it would do in terms of solarly growing these vegetables?
Those are great questions. So for your first question, right now, there's no way to cook anything on space station. They don't even have a microwave. They have some hot water up there, so that's it. So for space station, we're really looking at supplemental salads that can go along with the packaged diet. We've done a lot of work over the years here at Kennedy Space Center. My colleagues have been doing this for probably around 3 decades now, maybe even a little longer, looking at other types of crops, including staple crops such as potato. There's been a lot of potato that's been grown, things like peanuts, soybeans, wheat. So there have been a variety of crops that have been looked at for longer duration, colonization. But you'd need to take a lot of equipment if you're going to grow those crops. You'd need things like, a microwave, an oven, maybe a bread machine, a flour mill, a tofu press. So that would be pretty far down the road from where we're at right now. Right now, we're looking at things that could be eaten fresh with very minimal processing, minimal additional crew time. But all of those things are going to be necessary if you want to do a long-term colonization, which is, one of our ultimate goals is space colonization. So it's definitely something that's in our minds, and we're looking at that. We're also looking at specific nutrients to help augment the packaged diet right now, things that you could grow fresh and eat that, maybe some vitamins are low or they don't store well over time. So for a long-term, mission to Mars that may last, a couple of years, then you might have this fresh produce as an aspect to your diet. In terms of what you could have on the surface of Mars when you get there, you could certainly do a pre-deployable greenhouse. There have been some concepts and ideas for things like that thrown around. The incoming solar radiation to Mars is a lot lower than what it is on Earth, and then with things like dust storms, potentials for micrometeorite impacts, I'm not sure you would want to be on the surface with a transparent greenhouse. There's also damaging UV radiation that would damage a lot of our transparent materials. So I think it's more likely, at least in the near future, you would have maybe an underground protected structure. Possibly you could use light piping to pipe in some of the sunlight, and then you would use electric lights like we're using on space station to grow the plants. But I think all of those things are definite possibilities. Thank you.
Thank you, Joya. That's all incredible work. Do we have any more questions in the room? We have time for one more. All right.
Thank you. Is there a difference in the way plants grow on Earth and how they grow in microgravity?
That's an excellent question as well. There are a lot of differences that go on, on the cellular and the genetic levels, and a lot of my colleagues are doing, some incredible research to really untangle and find out what those differences are. From a large plant perspective for crop plants, the main difference we've really seen is dependent on the environment and the behavior of water and air. Fluids kind of form a ball, and water and air don't mix really well, so watering your plants is very tricky. So if you can get those environmental conditions pretty satisfactory, plants will grow pretty well. They don't have gravity as a signal, but they'll key in on other things. The shoots will grow towards the lights. The roots may grow towards, water, pockets of nutrients, and air, gradients of moisture. But they actually will do okay if you can get that environment right in terms of food production. But there are a lot of differences that are going on, on a much smaller scale.
Thank you so much, Joya.
Thank you.
Next, we'll hear from Kasturi Venkateswaran, Principal Investigator for Microbial Observatory 1, as well as the co-principal for Micro 10, and he's from NASA's Jet Propulsion Lab. Venkat, your experiments will help us understand crew health and equipment during long-duration spaceflight. Can you please tell us more about them?
Thank you very much for the introduction, Cheryl. And it's a great segue that, how the plants are growing in an environment. So at the same time, we have to come up with the appropriate conditions for the people, astronauts live in there, because they are going to breathe in and breathe out. Our first video, please. So this is to monitor environmental microbes associated to the closed system. So that doesn't mean that NASA has not maintained this so far, because in past 20 years, we do monitor the environment in terms of microbial contamination. But what we have done so far is the traditional old culture-based analysis, which can cover only 1 to 10%. But recently, National Research Council is telling NASA, hey, we are in DNA era, so you have to utilize the state-of-the-art molecular technology so that you will be able to comprehensively come to know what is there that the astronauts are breathe in and breathe out. They have to live, if you think about journey to Mars, few days of coming back is not possible. But from space station in few days you can come back if you have any problem. But this is the first time that we are collecting samples from space station utilizing sophisticated technology, and those things are not yet to be processed up in the station. I think some of the other technology is going to be shown today about the genes in space, may be helping us to monitor those things in the space. But right now we are bringing back with the whole suite of molecular technologies. We are going to see what is in there to get a baseline study. To get a baseline study, it's not going to be only once, so you got it done. It is not like that. Like our home, we have to maintain multiple times, clean and clean and clean. So while we are doing that, how these microbes survive. So we need to have microbial succession study. So we have a series of experiments from in our project, 3 different time periods, once in every 3 to 6 months we are collecting. We already collected 2 samples, and this is the 3rd set of samples. We go back to the exact same locations, the exact same place, so that the routine maintenance they do, but we also tell them that don't clean before the sampling. So we tell them to clean at least 4 or 5 days before, so that we know what is the dropouts, what are the particulates accumulated in an area, so that we can get an idea using suite of molecular techniques. Now you need to know, you can see what are the things are really viable that you cannot culture that may be problematic for the health, so that you will be able to get into a countermeasure development that would enable for a long-term journey to Mars. Next, can you show the photo, please? This is an example. So far I told you some of those things are, not only what astronauts are breathing in. So we are all breathing in good and bad, right? So we are also exploiting in our, the second one, Micro 10, we are also exploiting the beneficial microbes that we are seeing here for a future countermeasure development. So one of the fungi we are flying in the same SpaceX 8 in a different payload where I am the co-PI. So we are sending the Aspergillus nidulans that exhibits production of secondary metabolites which can be exploited as a medicine for future. So these fungi actually under stress will produce something. So we did not get any wonder drug after penicillium yet. So we may be able to see whether anything like that up there, so under the microgravity, whether anything is being produced differently that can be exploited. So first experiment, which is microbial tracking number 1, we are getting a baseline and see what are there, good or bad, and if we have anything that we are taking it to beneficial level, which is our Micro 10 experiment. Thank you very much.
Thank you, Venkat. We will now go to questions. If you're in the room, please raise your hand to ask a question and we'll bring you a microphone. As a reminder, if you're listening on the phone, please press *1 at any time to enter the queue. And if you're following us online, please use the hashtag AskNASA to submit your questions.
Mark Gotch, Historical Space Imagery. Yes, sir, very interesting. Can you tell me, microbial bacteria, when astronauts are leaving the planet Earth and going up to the space station, the bacteria they bring, flu-like, cold-like, etc., do they thrive in a zero-gravity space atmosphere, or do they perform negatively? Also, in the future, could we be looking at such a thing as a Mars rover sent with the capability of capturing microbial bacteria to be analyzed for the future for astronauts on Mars?
Those are very, very good questions. So I'll answer the second one first because that's how I started my life in NASA. So we are in a group called Planetary Protection. We are responsible to take a cleaner rover to this spacecraft, not to compromise the science. So while you are looking for lives in other planet, when you are exploring life in other planets, better don't hitchhack some of the bacteria that you are working with you. So that is one of the biggest challenge that we have whenever we land Mars. We make sure and clean the spacecraft to the level that will not proliferate. In other words, the red planet will not become green to the level that we are cleaning it, okay? So that is the conditions I'm working right now. So that's a very good question. We are developing technology, genetic-based technology. If you have a DNA-based life in there, we are capable of detecting it now. But we do not know whether the life in Mars and beyond is DNA-based. So that is what Mars 2020 is going to get the samples back to us, to the Earth, after a Mars 2020 mission, which is somewhere Mars 2025 or 2030, we will get the sample back. Then we will come to know whether we have to look for carbon-based or something else. So until then, we do not know how we are going to look, life in Mars. So the first question is, astronauts like us, we are all living fermenters. We outgas ourselves a lot of bacteria while we are walking, we are shedding, we are, sweating and all. So we are actually shedding those things. That is the part of life. But when you are living in a cramped, closed system, how well you have to keep yourself. The bacteria that I have in myself, maybe I am immune to it, but not to the coworker. So that's why you have hospital syndrome also. The people who are going to visit the patients may acquire something, so unless your immunity is better. So you take your whatever bacteria with you. So if it is flu, you know the symptom before you go. But if not, you definitely do. And the other work that is going on in NASA for the past few years are how virus reactivate under stress. So it is latent in you right now, but because of the stress, when you are under the microgravity, actually astronauts shed more virus which are otherwise latent. I think I answered your question.
Thank you, Venkat. We have a handful of guest speakers for our next presentation, so while they join me on stage, let's take a look at some of the research from the Center for Advancement of Science in Space, or CASIS.
CASES was created to provide access to a whole group of non-traditional space users that can use this one-of-a-kind platform for research and technology development, doing types of projects that literally you can't do anywhere else on Earth. And that's what's so exciting about our partnership with Lilly. They reached out to all parts of the organization. We went through a brainstorming, and through that process, we have 4 projects that will be flying to the International Space Station.
Kind of the guidelines for our interaction with NASA and CASES was that we would not do it if it wasn't of value to them, and we could not see the value for ourselves. You know, it would have to be something ultimately of value to mankind.
It's all about caring, and then it's plus discovery. We wanted to make sure that whatever experiments we came up with could do that, and this gave us an opportunity to do it in space.
The purpose of crystallization microgravity is essentially to grow more ordered crystals that we can then study. By being able to crystallize these proteins and have a structure of these proteins, we're then able to have a better idea of their function.
My role is as a research scientist in our discovery group, looking to see how their muscles and bones actually and other organs atrophy during their time in space, and it actually will be also looking at ways in which we could potentially prevent that occurring.
So lyophilization is essentially the process of freeze drying, and it's a process that's used across multiple industries, one being the pharmaceutical industry.
I typically use lyophilization as a tool, while Evan, he comes at it from more of the drug product.
You can think of lyophilization or freeze drying as 2 main parts. There's freezing, followed by drying at low pressure. And which process does gravity play a larger role in?
Lilly is fundamentally interested in the dissolution of tablets. It's part of really our core business.
If you think about tablets or pills that are ingested, they need to dissolve out as well, and you probably don't want them to take multiple hours to dissolve if they're supposed to be a quick release.
Working with companies like Lilly, where they're focused on discovery, is a great match for the International Space Station.
So I'm very excited to be sending some experiments up to the International Space Station, and it's been a rolling ball of enthusiasm and excitement.
The number of individuals who are involved in that and all coming together to make this mission really work, it's phenomenal.
Now, Ken Shields, Director of Operations for CASES, will introduce the Eli Lilly and Company team, and he will explain to us how these investigations will benefit those of us on Earth, as well as our journey to Mars.
Thank you, Cheryl, and really it's a pleasure to be here today. This mission, this SpaceX 8 mission, marks a significant milestone. It's the return of the Dragon capsule going back to the International Space Station, and the Dragon is a real workhorse for our national lab utilization. So for us, CASES, Center for the Advancement of Science in Space, the organization that manages and operates the International Space Station's National Laboratory, this is really a significant event. And it's a real pleasure to be here today sharing with you what Eli Lilly is doing on station, but also the diversity of what our portfolio and this manifest represents. As far as science types, we've got disciplines, physical sciences, life sciences, technology demonstration, fluid dynamics, and even STEM and educational outreach. In addition to the diversity of the sciences and the science types that we're flying, the organizations that are flying are extremely diverse. You saw a fantastic video here about Eli Lilly and Company and the projects they're flying. You're going to hear more about that here in just 1 second. In addition to that, we've got academic organizations, nonprofits. It's just a wonderful way for the National Lab to demonstrate its utility, its effectiveness, and its potential as a platform of innovation for a wide array of interests and organizations. So please pay close attention to what we're doing with the lab. I think you're going to see a lot of good that comes out of science and space for life on Earth. Now it's my pleasure to introduce the team here from Eli Lilly. Starting at the far end, we're going to have Mike Hickey represent, then also Christopher Gonzalez DeWitt, and last but certainly not least will be Dr. Rosamund Smith. So with that, Mike.
Yeah, thank you, Ken. On behalf of Lilly, we just want to thank you for the ability to be able to collaborate with you on this mission, SpaceX 8. And, it's kind of a dream come true for a lot of us scientists to be able to be part of what, you're enabling for us to send experiments up like that. And it's just great. It kind of goes hand in hand with discovery and the innovative spirit that Lilly has. It's made it the competitive pharmaceutical company that it is today. I happen to be a scientist in structural biology, and I typically find myself working on projects that have to do with oncology. And my field of expertise is in crystallization, so I've decided that what I'd like to do as far as seeing some change go on in the work that I'm doing here on Earth is, and the roadblocks that I'm having, is to try to do crystallization experiments in space. And so, well, what is a crystallization experiment? Really, it's where you're essentially employing what the pharmaceutical term would be a structural-based drug design, where you're basically identifying a disease or a cancer, you might say, a type, and you identify a unique pathway. And within that pathway, there might be a molecule of interest that's unique, and you're targeting that molecule. And you're designing a compound through many iterations to specifically bind that molecule to render it ineffective, to stop it. And in that sense, you're going to maybe even slow the progress of the cancer that you're looking at, or stop it completely. And so that's our purpose, and that was what I decided that I wanted to be a part of as far as this mission was concerned, because I'm involved in a project right now that, well, it's pretty important. You think, well, what's the impact of what you're doing? Well, I think the statistics will speak for themselves. 1 out of 20 people will get colorectal cancer this year. And in 2015, it was the 3rd most common cancer in the United States. And so that happens to be the target that I'm working with preliminarily. And what we want to do is try and see if space, or growing these crystals with compounds together where they bind each other, will enable us to get past current roadblocks that we have on Earth. Right now, we're fighting issues with lattice forming, sedimentation effects, convection problems, and these are things that can be mitigated in microgravity. And so that's what made this project really very valuable to us. And as I mentioned, you know, the stats there for colorectal cancer. And so you might say, okay, so what makes this different, Mike? Because we've seen other crystallization experiments go into space. Well, number one, this is only the 2nd protein, to my knowledge, human membrane protein to actually go into space for crystallization. Secondly, this human protein that's being crystallized with our compound of interest, it's really a tool compound at this point because we're looking for successive iterations through structural-based drug design. It not only is implicated in colorectal cancer, but in a variety of other cancers as well. So it has a huge platform. It has a great, it's an entirely great druggable target. So we're excited about it, and we have some examples for you up here. We can talk about these in detail certainly offline, but I wanted to show you one here in particular that we're actually using on this mission. This is called the HD-PCG device. It's on loan, and thanks to CCAFS for enabling us to be able to use this, but it affords us ability to send up 30 crystallization experiments in space. And the beauty of this, if I can show you, is it allows, actually, could you hold that, Chris? It involves the astronauts. They've got to come in on a timely basis, remove this small tool, and rotate this a certain direction at a certain time point at the beginning of the mission, and at the end of the mission, they rotate this back again and shut off the experiment, and then splash down, we retrieve this, and then we open it up, and what we see on the inside, interestingly enough, we've got 6 rows of experiments like this that we can look at and see how this fared based on similar experiments that we did here in 1G, here on Earth, and see if there was a marketed improvement in crystallization. So I'm excited about it. I can't believe I have this opportunity. I'm looking forward to future opportunities with you, Ken, and with CCAFS, and I think I've said enough here, so I'm going to let Chris talk now about what he's doing.
I too, like Mike, am pursuing a crystallization experiment to aid structure-based drug design. And I think really the distinguishing feature of our experiment is that we are pioneering a new tray type. It's called the in situ 1 crystallization plate. And we're really excited to feature this because the hope is it does hold 96 individual crystallization drops in this plate, and in a much smaller footprint than, let's say, the handheld high-density protein crystal growth apparatus. And we're really excited about this because it's commercially available. It could be purchased by any crystallography laboratory, and we hope that with the success of this, because this will be the first mission that this plate will fly on, that we'll be able to make crystallization experiments more accessible to a broader audience of crystallography researchers.
Okay, my name's Ros Smith. I'm the principal investigator for the muscle wasting experiment. And the goal of our experiment is to see if a novel Lilly investigational compound will be able to prevent muscle wasting in space. And we're going to use mice as our experimental model for this experiment. I think you're aware that in space, muscles atrophy and waste. The astronauts experience that. So obviously this experiment has implications for, space flight and longer-term space missions. But for us, the interest is because of patients on Earth who have muscle wasting diseases. This can be things ranging from ALS, muscular dystrophy, certain types of cancer, and even the frail elderly undergo muscle wasting. And there are many similarities between the muscle wasting that occurs on Earth in those diseases and that occur in space. We're excited to run our experiment in space because under the microgravity conditions of space, where there is no loading of the muscles, you actually get a global effect on of muscle wasting on all the muscles. And so this is a unique feature that's very difficult to make happen on mice on Earth. So we're excited to do this experiment in space, and it's a unique feature. There are several unique things about our experiment, not only the compound that we'll be testing, but also for the first time we'll be measuring the actual function of the muscles of the mice. Normally, often we just, in previous experiments where mice have flown, they've looked maybe at the size of the muscles, but this time we'll actually be sending up a special piece of equipment where we can actually measure the function of and the astronauts will be helping collect the data to measure the functions of the muscles on the mice. So we're very excited. We hope to get the results from this experiment and integrate them into our discovery efforts to try and find new ways to help patients on Earth who have these muscle wasting diseases.
Thank you all. Appreciate the lab coats and the show and tell you had for us today. If you're in the room and you'd like to ask a question, please raise your hand. We'll start over here.
Is kind of a multiple question. Is this the first time Lilly has done this in space? How long will the experiments last, and how much is it costing the company?
I can answer. First of all, it is the first time that I'm aware of that Lilly is doing this in space. And for the muscle wasting experiment, the actual experiment is going to last for 6 weeks. I'll let Mike and Chris comment on their experiments. And maybe Ken will answer the funding question. Do you want to ask how long your experiments are going to last?
Go ahead, we're the same.
So our crystallization experiments will be up there for about 30 to 35 days, or pretty much for as long as Dragon is birthed at the International Space Station. And so once Dragon descends to Earth, our crystallization experiments will be on the space vehicle, and then it'll be unloaded and we'll retrieve it.
Yeah, so that's a great question about the cost and the funding. And all of these Eli Lilly projects are a great example of how the ISS National Lab is really, I think, a perfect collaborative platform for a public-private partnership for science and discovery and doing R&D in space. Eli Lilly is covering all of their internal costs as it relates to PI salaries, laboratory supplies, all of the costs that have traditionally been covered vis-a-vis maybe a NASA grant or an NIH grant are actually being covered in a very commercial way by Eli Lilly. What is being provided from sort of a subsidized way is the upmass, the launch of the ISS, the use of the ISS, like all of the other investigations that go to space. So that's my attempt at trying to explain the cost, if you will.
Do you have a dollar figure of what it's costing Lilly? Just anybody know what it's costing the company? I'm just curious.
I'm sure the company knows. I don't know exactly what that figure is, and I don't know that Eli Lilly would be willing to share that right now.
That would be correct.
I didn't want to speak for Lilly.
Thank you all. I believe we have one more question from the gentleman in the front.
Thank you. Mark Gotch, Historical Space Imagery. Once again, I think the world needs to be very thankful of CASE's original creation And once again, we look at the opportunity that CASIS is giving a private business and private individuals that you have brought forward to do experiments in space. To ask your question involving your muscle research, how would you expect that differences from what you've learned on Earth in muscles that are atrophying, your experiments being done in space, how would you think that it will affect and changing that medication by what you may learn in space?
Well, as I say, this experiment in space actually is a unique way to give our mice a global muscle wasting. That's very difficult to achieve in our models normally on Earth. So we haven't been able to do that to date. So what is unique and very useful to us is this global muscle wasting, because many of the diseases on Earth are often affecting all muscles of the body. So that's the unique part that we wish to answer the question, how our compound works in that environment when one has that type of muscle wasting.
Thank you all. Next, we'll hear more about a student-led DNA investigation.
So now I'm taking the samples that we prepared and I'm getting ready to actually run them in the PCR machine. I'm Anna Sophia Bagyurayev and I'm 17 years old. My experiment looks at the genetic sequence in space to see if any changes in our genetic sequence might be related to some immune system difficulties that astronauts face. We use this mini PCR machine to make multiple copies of the DNA sequence that we wanted. For astronauts who, especially if we're looking to do long duration space flights in the future, the International Space Station, while it's definitely far away, it's much closer to Earth, much more connected than a Mars mission or a deep space mission. So by understanding these markers, we can possibly then understand more about the immune system in space and potentially keep astronauts healthier. Just knowing that maybe I'm not in space yet, but a little piece of me is, and not only is a little piece of me going to space, it's also potentially helping the future of space travel, the future of mankind's. That's a really powerful thing to me, and I can't wait to watch that rocket launch and know, there we go.
You probably recognize Anna Sophia Bagyurayev, student researcher from our video. She has joined me on the stage with Mark McQueen, ISS program manager for the Boeing company, to discuss Genes in Space 1. Mark, over to you.
Okay, thank you very much. It's an honor to be here. Boeing is very proud to be NASA's prime contractor for the International Space Station. Today, of course, it's sustaining operations, integration of payloads and science and other elements. It's also subsystem management, make sure all the systems are operating. So it's a lot of activities going on currently. As we look to the cusp of the one-year mission with Scott Kelly coming down, understanding the long-term effects of zero gravity, of space travel to our crew, it is very important for us to understand that. And we were looking with other companies, with CASIS and others, for one of our science, technology, engineering, and math, our STEM project, what's the right thing to do? And what we said, well, long-duration space travel is here. It's coming. It's going to be in the next 5 years where we're going to be going to Mars and other places past the moons. And so if we understand the effects of space travel on our DNA of the humans, we can better prepare our crew for their space travel. And when they come back to Earth, they have a better life. Space travel is going to be 1 to 3 year missions for these things. So it's not just the short durations that we're used to, 6 months, or even Scott Kelly's 1 year mission. These will be long space travels, so the better we understand it, the better off we are. We had 330 proposals from students from 7th grade to high school. Very impressive. It was, again, the proposals were on how DNA, how they could affect the exploration effects of the human DNA, and these students put together different proposals. We put a team of experts together to select from those proposals, industry experts, not just from Boeing or anything like that. And we picked the best of the best that we think is very applicable. And to our credit, we got a very dynamic person who was also selected, and we're very proud of Anna Sophia, so I'll let her explain her experiment.
So, hello, I'm Anna Sophia, and I'm basically a girl with a box. This is my box. It's a mini PCR machine. So PCR stands for polymerase chain reaction, which is essentially, it's a pretty standard lab procedure where you'll take little pieces of DNA, put them in these tubes, mix it up, and then the chemical reaction that then occurs in the machine essentially photocopies the DNA. So you amplify it so you have increased copies of the sequence you want to look at. And this technique allows you to look deeply into the genetics of various processes within the body. Now, though it's a standard lab procedure on Earth, it's never actually been carried out in space because typical standard PCR machines are very large, bulky things. But when Mini PCR designed the small machine, that's then what led to the contest that was just spoken about. And when I looked at it and I was thinking, well, what would I do with PCR in space? I actually didn't go directly to just looking at the genome. I went to another layer of the genome called the epigenome. So an epigenome is a layer of extra kind of markings you can have on your DNA sequence that also affect how genes are expressed. Now, I was looking at the epigenome, so these little markers, in relation to astronauts' immune systems. When astronauts go to space, they tend to experience problems with their immune system. And reading up on this, I noticed that there was a lot of similarity between the patterns I was seeing that the astronauts were expressing and things that had occurred on Earth when aberrant immune system phenotypes were caused by changes in this epigenetic pattern, so changes in these markers on the DNA. And I thought, wow, what if we can use the mini PCR machine to essentially monitor astronauts' immune systems by looking at these little markers? But of course, because it's never gone up before, we have to make sure that the process works. So what's flying, hopefully tomorrow, is going to be basically just a test to see if the standard procedure we use to look at DNA and then these markers, so these methylation markers, these epigenetic markers on the genome, to see if that process works in space. And if it does, then we've got this whole new window of insight into human genetics in space that we've never had before, which will lead to a bunch of, a huge amount of innovation, but most importantly, a significant increase in autonomy from the Earth. So we won't have to be connected to the Earth. Astronauts can be much more aware of their immune system. We can be aware of defects that are going on in other body systems. Epigenetics is related to many body systems, and this will all be able to be done on the space station. So now we're free. We're slowly cutting the tethers we have to Earth, which is going to enable long duration space flight and extreme future innovation. Thank you.
Thank you, Anna Sophia. Ladies and gentlemen, she is 17. So remarkable. We'll open up the floor for questions. Start up here up front, please.
Mark Gotch, Historical Space Imagery. Yeah, it's a very good presentation. Can you tell me, did you develop that microbial machine in its compressed smaller size? As you mentioned, there was a much larger machine atypically used. And in looking at the microbial tests that you are going to do you expect that the results will yield to being able to address astronauts falling prey to what is happening to them with longer periods in space?
So for the first question, no, I didn't design this machine. It was actually designed by a company. It's Mini PCR, so same name as the machine. So they're the ones who downsized it. A lot of it was for educational purposes. They're a big educational outreach, and that's also why I'm here. And the second question, so were you asking just, do I expect to see that it works? Do I expect to be able to use it in the future?
How do you expect it to differ from what they found occurring on Earth compared to the astronauts and their condition as time and duration of their mission goes on?
So procedurally, I expect the technique to work the same, but what I'm looking at eventually in the epigenetics is I actually expect, so the way epigenetics works is you'll have cells you'll have cells differentiating, and the way what controls if they turn into one cell type or another is a lot affected by these markers. So if the markers are there, it'll turn into cell 1. If the markers aren't there, it'll turn into cell 2. One of the things that we've seen in space is we have these T cells, which are part of the immune system, and T helper cells can differentiate into either T helper 1 or T helper 2 cells. On Earth, we have a relatively balanced T helper cell phenotype. In space, we see a significant shift towards a T helper 2 cell dominant phenotype. So for that process, I'd look at the regions where the markers occur in the T helper cells, and I'd see if the marker pattern was the same as we see on Earth. I wouldn't expect it to. I'd expect us to see significantly more markers that encourage differentiation towards T helper 2 cells, and these markers can be changed. It's been shown these markers can be changed by microgravity. They can be changed by potential cosmic radiation. So I would expect to see that change, indicating the source of the aberrant immune system that we see in space.
Thank you very much. A question well answered.
Thank you both. Now, our final guests today are Jason Cruzan, Director of NASA's Advanced Exploration Systems Division, and Robert Bigelow, President of Bigelow Aerospace. But first, let's take a closer look at the BEAM, the Bigelow Expandable Activity Module.
NASA is developing the capabilities to send people into deep space. To accomplish this, we need to extend our knowledge of how to operate in space. NASA is developing habitation systems that provide safe and sustainable space-based living quarters, workspaces, and laboratories. Expandable habitats are one option. These potentially weigh less and occupy less volume on a rocket while allowing for additional space for living and working. However, testing needs to be done on the design performance of expandable habitats. The Bigelow Expandable Activity Module, or BEAM, developed under contract with Bigelow Aerospace, provides a test platform for demonstrating the thermal, structural, radiation performance, mechanical durability, and long-term leak performance of expandable habitats. The BEAM will be transported to the International Space Station inside the SpaceX Dragon supply vehicle's trunk. Once Dragon is berthed to the space station, flight controllers at Mission Control in Houston, Texas will maneuver the station's robotic arm to extract BEAM and attach it to the rear port on the Tranquility node. After all preparations are complete, crew members will begin inflating the structure. This will be the first time an expandable habitat has been deployed on station, so the procedure will take place slowly to closely observe the expansion process and maintain the safety of the crew and the station. During this time, BEAM will expand from its packed dimensions of 5.7 feet long and just under 7.75 feet in diameter to its pressurized dimensions of 12 feet long and 10.5 feet in diameter. Once BEAM is fully expanded, the crew will pressurize it and test it for leaks. After this, BEAM's pressure will be equalized with the station pressure, and the crew will enter the BEAM and install sensors. The ground-monitored sensors will autonomously collect thermal, impact, and radiation data throughout the 2-year on-orbit life of BEAM. These experiments will help determine whether expandable structures will provide a viable, lightweight option for future space habitats.
Jason, Mr. Bigelow, thank you both for joining me today. If you don't mind, can we start with one clarification? Inflatable versus expandable. Is there a difference?
So yeah, we get this question quite often, both on the NASA side and on the Bigelow side, and it is good to differentiate between the two. The simple answer is inflatables make you think of things like balloons and those kind of things that don't have a structure in and of themselves. You inflate them, it loses air pressure, and it instantly collapses down. An expandable structure is more like a tent. You think about in a pack configuration, it fits neatly in your car and you're in a backpack. When you go to a site, you set it up. You can open the windows. You can get in it, get out of it. It keeps its structure at that point in time. So we tend to call things of this nature expandable because of that kind of the rigidity of the device. If something were to happen, it actually still maintains its physical structure even after even reduced air pressure that they have as well. So with that kind of initial question out there, I'm going to touch on 3 different things. First is, why do we need habitation? Which may seem like an obvious question. The second, talking about the potential use of expandables, and then a little bit about our demonstration that we're doing on board with this flight experiment. First off, habitation. So as we send crews off to faraway distances like Mars, you heard mention of other folks on the panel here talking about mission classes of up to 1,000 days, 1,100 days. With that, we need a place to live. We need a place for logistics. A round trip to Mars may take us up to 300 cubic meters in storage volume for both the live-in and all the goods that we have. So we need a very large habitat to live in. Why expandables? So to date, everything we've ever flown has been metallic structures. We have a wide understanding of metallic structures, but there are limitations to metallic structures in that the largest thing you could ever fly is what fits in the rocket's fairing. It's never going to get any bigger than what you have in the fairing size. And again, getting back to that 300 cubic meter size volume that you want. So we've always considered expandables. That's why NASA did the original investment in Transhab, but we had never actually gone all the way to flight. So with the beam module that we're flying here, we're actually flying a higher factor of safety on that because of our unknown knowledge about expandable structures. But specifically, we want to understand the structural integrity, the radiation performance of these, and the temperature controls of beam in order to actually help inform our choices for deep space habitats. So we're going to do that over these 2 years. So with that, I'll turn it over to Bob to actually talk about how did they actually build this module.
All right, so as Jason says, our heritage is from the NASA Transhab program, and we became enamored and enchanted with that architecture and saw its potential. And so if I could go ask for the first slide, please. That's our home base in North Las Vegas, Nevada. It's situated on 50 acres. There's 365,000 square feet of manufacturing and fabrication and design space at that facility. And that's where everything is made. We function as a general contractor. About 50% of all the hardware that goes into any of our spacecraft is created there. And we subcontract out for other hardware systems from other companies. So we don't make everything. It's about a 50-50 kind of balance. Next slide, please. And that represents the beam before it was sequestered in the trunk of the Dragon. And as you can see there, it's not terribly large, kind of a layer cake sort of fashion. It is a different shape than we were used to. We flew 2 prior missions, Genesis 1 and Genesis 2, thanks to the Russians in 06 and 07. And those had to be configured to the shape of a fairing. This had to be configured to the shape of something much different. Half the size of, or half the shape maybe of a soup can. And so we had to come up with a way that was practical to orchestrate that, to fit in that enclosure. So it suggests that you may have other kinds of challenging enclosures, potentially, that you could still adapt to expandable systems. Next slide, please. This shows it going into the trunk of the Dragon. Next slide, please. And of course, there's the Dragon and the trunk itself. And as you can see, the configuration of that. Next slide, please. There's the beam by itself showing the docking adapter system. And the little kind of antenna-looking thing on the end is what the Canada arm is going to grab onto to be able to secure itself to the beam and remove it from the trunk and then put it onto node 3 for berthing. Next slide. That's a perspective of size. Roughly a 6-foot-tall person adjacent to the beam. Next slide. That's a transparent system or portrayal of what the interior looks like. It's quite empty, as you can see. And the thing I want to impress here is that the beam is an experimental spacecraft. It has this type of architecture have never been flown before. It has been bound up for over a year, waiting for launch. We're not 100% sure of its behavior. It is a testing station. That is the whole point here. In all respects, not only in monitoring what is the environment inside going to be like and radiation exposure and defense against certain kinds of things, perhaps debris maybe, or certainly radiation and temperatures, but it's also potentially may even someday NASA might give permission for some kind of a commercial application to be operated inside. We don't know yet. So it is a testing facility. It's human rated. There would be people inside periodically. So it has its unique spacecraft. Next slide, please. And this slide shows it's being attached to node 3. So you can see the size is quite a bit smaller than the node 3 itself. It's the beam is 16 cubic meters as opposed to our B330, which is 20 times larger, 330 cubic meters. Next slide, please. And that shows where we hope to have, by 2020, 2 330s ready for launch. This shows them with a CST-100 on one end and a Dragon on the other end. So we are sort of politically correct there. And, and anyway, that represents 660 cubic meters of volume just with those two habitats together. And that's what we hope to deploy sometime around 2020.
Thank you, gentlemen. We'll go to questions in a moment. As a reminder, if you're in the room, please raise your hand to ask a question. If you're on the phone line, please press *1 to enter the queue. And if you're following us online, use the hashtag AskNASA. Now, first I'm going to invoke my moderator privileges, and we have two models up here. I was hoping, Mr. Bigelow, can you explain what we're looking at?
Sure. Of course, this is the beam structure here that we have, and this is a 330. The 330, as opposed to the beam, is intended to not rely on any other spacecraft for sustaining life. It is essentially a standalone space station in and of itself. Contrary to the beam, requires complete assistance. It is an enclosure, but it's lacking avionic systems, propulsion systems, ECLS systems. So it is much different than the much larger system is.
Great, thank you. Any questions from the room? We'll start here in the second row.
Thanks, James Dean, Florida Today. Mr. Bigelow, how important is BEAM to achieving your 2020 hope for launching a private station? Is this mission essential to creating the confidence for customers to sign up for a station like that, to signing launch contracts, or is it more about showing NASA that this is a deep space technology?
Yes, all of that. No, we're seriously, it is an important step to us. It really is. That NASA has the confidence in our little company to be able to do this. We are very proud to be able to actually get to a point of deployment on a type of architecture that was begun in the 90s. Although expandable systems go way back, decades before that, still in the 90s, it really got serious because NASA at that time was looking for enclosures that were safe and large to take people to Mars, in theory. So it's kind of come full circle now. So we're excited about this opportunity. We do hope that it does lead to other extensions of relationship, that we have with NASA.
I'm sorry, just a quick follow-up. 2020, are you talking about a private station for some customer other than NASA, or is that something NASA would be participating in as well?
We're working on a combination of things.
Dan Billow from Channel 2 for Mr. Bigelow. You talked about generically some commercial applications. What do you mean? What are your dreams? What could result here? What kind of commercial applications?
Well, our business model is essentially, my background is in development and construction and general contracting and banking and everything to do with real estate. So I transfer a lot of the business case from that industry, and essentially the foundation of our business case is time sharing time and volume, and branding, which includes anything from naming rights to all kinds of advertising or whatever, the kind of thing that you would see perhaps in the case of income streams in universities. You have naming rights for lecture halls and wings of buildings and the building itself, and then eventually the college. And so all that's applicable to structures in space that are commercially operated. We would operate these on behalf of nations who have astronaut corps and others that aspire to have them. And right now, the frequency of opportunity to fly is not often. Other than for the United States and Russia, it's about once every 3 years, close to that. And some countries maybe never, or very, very seldom. So there is a substantial appetite out there, we've discovered. And so we think that's a market. The corporate world, like Lilly, for example, certainly is any material science, organic or inorganic, is absolutely mainstream in our thinking, that we would very much want to host those folks. So it's a combination of everything from what you could manufacture product-wise and send down. It could be information you're sending down, not just a hard piece of material of some sort. It could be national image. It can change an image of a country overnight to have that kind of facility, or to induce Lilly to locate their plant in their country and offer them that kind of a resource in orbit as a very unique laboratory. And naturally, NASA could be a very important customer to that kind of an industry, and help to save NASA money and be able to spend money for just discrete periods of time and a certain amount of volume that is really what it needs. Not having to write a much larger check to buy the entire thing. Why do that? So our model is trying to propagate the opportunities among the largest groups of folks we possibly can for the lowest nominal cost that we can.
Hi, can you explain how exactly the beam will be expanded, whether it be via pressure or mechanical or some combination of the two?
Yeah, so after the beam is birthed to the space station, the initial pressurization of it will be handled through what we call the intermodule fans, IMV fans. These are precision fans that move actually air between modules on board the ISS. So within Node 3, there's IMV fans that will actually flow air into the beam module. That'll get it up. It'll allow it a very controlled expansion of it, because we don't actually know which way it'll expand. Our models say one thing, but models are models. So we want to actually very slowly and carefully start that initial inflation. And then once we get up to a nominal pressure, then we'll actually open up the tanks that are inside of beam and bring it up to the full station pressure. Beam is carrying enough replacement gas to basically inflate itself. So we'll make up the gas back to station after we finish the inflation sequence. So it's gas neutral for its entire expansion.
Thank you. We'll go all the way to the back.
Thanks very much. With Reuters, I have a few different questions. First, for Mr. Bigelow, after launch, what in your mind is going to be kind of the most critical parts of the mission? And are there any contingencies if there is some issue with it unfolding or something else where the whole module could be jettisoned? In other words, what kind of plans do you have for that? Let me start with that. Thanks.
Well, I think my personal opinion is my focus is on SEALs. Whether it's a submarine or anything that is an extreme environment, you want to be able to protect that enclosure. So whether it's, in this case we don't have windows, but whether it's in our B330 we have 4. So whether it's hatches and bulkheads or windows, my first focus is on the successful functioning of all of the seal mechanisms. No, so I'm not worried about the hull. I'm not worried about anything to do with that. I'm working about the interface between metallic systems and soft goods systems. It's a very complex interface. So that'd be my first concern. If I were a drinking fellow, my first concern might be going to the nearest tavern, right after launch, saying, thank goodness that, it passed that, but I'm not, so.
And then your second part of your question on contingencies. So yeah, there are contingencies on the outside of, in the most extreme case, we have the ability to potentially go out and even conduct an EVA to help with the assistance of removing strapping and those kind of things on the outside. We have multiple ways to inflate. As I said, we're using the IMV fans. We could also use the compressed gas that's in the inside as well. And in the most extreme case, if none of the options worked, we can jettison the module by using the robotic arm. But we don't envision that. That's plan F, several down the the scale.
And are you inflating with just air, regular air? And as far as the future beams, or would the $17.8 million roughly that I think NASA is paying for this, Mr. Bigelow, is that actually what you think these things will cost, or was that a special demonstration discount that NASA got?
I grieved for a long time over that low figure, believe me. So, it's no, that was a unique situation. As I mentioned before, our business case is to sell discrete periods of time and volume. So this was a very unique situation for us and for NASA, and we did try to accommodate NASA the best we could.
Yeah, and on the air question, it is kind of our, obviously the station air was standard station air. The air mix that's in the tanks is up to the same quality of air mixes that we fly on normal missions as well. So just happened to be sourced from Nevada though. So.
I understand the reduced volume of launching a collapsed module like this. That's an obvious advantage. Can you talk a little bit about the relative, the balance between not only the size but also the weight of the module compared to a typical hard body module? So those advantages, weight and size. Thanks.
Yeah, the advantage is tremendous, not just in volume but in mass as well, because per cubic meter, and that's how you equate it, right? So most of the modules on the ISS do not exceed 110 cubic meters. I think that's the largest that's probably on the ISS. So you're getting 3 times that per launch, and our mass happens to be around 43,500 pounds, and so that's a huge benefit.
Yeah, this is one of those things that it depends on the size. So something like beam was not optimized for mass. And in fact, it has a 4 times factor of safety, where our standard metallic modules are 1.5 to 2 times factor of safety. So we actually have gone overboard on protection and those kind of things because of our unknown performance of the vehicle. So as things scale, so if you had something like a Cygnus, which is relatively close in size, mass to volume performance is about the same. However, that's with the extra factors of safety, and you can't really compare those two apples to apples. But as you scale up to larger sizes, as Mr. Bigelow stated, that's where the advantages of soft goods really come in from a mass performance. The strength of material performance as well. If you look at metallics versus soft good performance, it's almost an order of magnitude from a material mass strength property. So there's a reason why bulletproof vests are made out of soft goods, not rigid materials, and it's a strength of materials and stopping power for that. And so you're really taking advantage of the material properties inherent in soft goods as well.
Thank you all. I believe we have some questions from online, so we'll take one for social.
Yeah, from social media, we have a question from John Ship. He's asking, does the material composition of beam pose any potential detriment to the overall solidity of the ISS as a pressurized habitat?
No. It's a simple answer. The external cloth on the beam is a beta cloth, which we use commonly on the outside, and all the other rest of the materials went through extensive testing for outgassing and such, and went through our standard approval processes.
And from Sophia, we have a question. Has Bigelow used any 3D printing of parts or components for beam, or do you plan to?
No, we have not, but we do expect that that's going to be a very valuable component to future spacecraft.
Right here.
Josh Dinner with the Orbital.Space. The beam is essentially made of cloth, and I imagine that is going to be a lot more absorbing of sound, of the ambient noises created by the station. And crews are scheduled to go in, I think, 3 to 4 times a year. Are they allowed to go in if they want some peace and quiet, so for instance, other times?
Yeah, so yeah, our nominal ingress strategy is about 3 to 4 times a year, primarily to retrieve data. We have data storage devices and those kind of things that are not hard plumbed into the ISS, so we need to go in and get the drives out and download that data. After a period of time, we really do want a quiescent period of time towards the beginning of the experiment to kind of get nominal data of its performance. In theory, we should be able to get that in about a 6 months time frame. There's nothing that restricts the crew from going in more often. It will be a relatively quiet area, but at the same time, we do air exchange inside of the beam. So it's not as quiet as you're thinking, because there's still air movement that's occurring in there, but relative to the rest of the station, it absolutely will be much more quiet. And there's no restrictions of them going in.
Thinking ahead, do you have any customers signing memorandums of understanding to lease time on the B330? And is there any federal law that would prohibit you from reaching agreements with certain governments who are interested, for example, China?
We are aware of favored nations and non-favored nations status, so we would not rub anybody's nose in that problem. Sorry. Yeah, so we are conscious of foreign relationships that we need to not turn into issues. Having said that, we have actually 4 different groups today that want to fly experiments and different payloads to Beam and deploy those within Beam. And they've been the 2 are countries and 2 are corporations. And we're hoping that maybe in half a year or something we can get permission from NASA to accommodate these people in some way. And so we have the element of substantial clientele, or us starting to collect deposits by virtue of reservations and that type of thing, has always been hostage to the availability of transportation. And we've had to throttle our own progress from different periods of time according to the ability of transportation to be there at a certain point in time. And our perception today is that we'll probably have maybe 2 systems in operation maybe in 2018. So we can maybe make the next projection that we should have 2 structures ready for deployment, 2 B330s in 2020. Correct.
We have a couple questions up front. We'll start here and work our way to Mark.
Hi, Thaddeus Cesare with the Utica Phoenix. I was hoping to get an idea of how and if this beam technology could change the evolution and design of the International Space Station. Should we see more of these being attached?
So at this point in time, we don't envision any major changes on our NASA side or even our international partners of the actual structure of the ISS itself. We do envision at some point in the future, how do we transition from the International Space Station to commercial low Earth orbit space stations? We're trying to figure that out between us, CCAFS, and commercial organizations like Bigelow. And how do we transition from an ISS-based operational model to low Earth orbit commercial space stations, where NASA is just potentially one customer of hopefully many? Does that involve going from space station to a module on station to a free flyer module? We don't know at this point. There's desires on both sides, so we'll have to figure that over the coming years.
And just as a follow-up, just hoping to hear about some of the design challenges, some of the issues in bringing this to fruition.
I think, well, I have to give a lot of credit to our success up to this point, to an incredible staff that we have at our company. We also received good advice from NASA in this process. So NASA was providing insight as opposed to oversight, which is an important distinction there. So we were allowed to proceed with the architecture and the full complement of structure on our own, in concert with NASA input here and there. But I think we had a good symbiotic relationship with our team of folks and NASA people, and we're hoping if there is a follow-on project that we can maintain that same group of people and that same spirit.
Yeah, from the NASA side, technical challenges, I mean, Bigelow and his team really were the champions in this and putting the modules together. We shared a lot of our material expertise and operational expertise. Obviously, the whole lessons learned from the ISS itself. I would say that the biggest challenges were not so much the development of the structure itself, but how do you do for the first time an expansion in space? How is that dynamically going to work? How are loads and models? We don't have models for these types of structures performing. So that unknown made us do a lot of homework. And then even on the unlikely circumstances of jettison, those kind of things, the things that you hope never happen, those are the harder things to kind of answer, is how do you remove a partially expanded module and then do basically a jettison at that point of something that isn't a fully rigidized structure. So those are probably some of the challenging aspects from it, but quite frankly, most of the actual manufacturing and design and all that was all Bigelow.
Gentlemen, I think everyone saved their questions for you. We'll go to one more with Mark, and then I think we'll have a final question after that.
Mark Gotch, Historical Space Imagery. Yes, very interesting presentation. Sir, can you tell me a couple of parts to my question? The Bigelow that is going to go up to the space station, I see it very much so being attached to it as a space that, let's say there were repairs or technology that were to be done on a smaller form, it would be well usable, that additional space. If I look at your last slide showing the space station image of two Bigelows put together, I want to ask you this. Currently, the space station, it's structured interior in terms of what it weighs. I know we are working in a weightless atmosphere, but how much could the Bigelows, two of them incorporated, entail in terms of structure, interior of what is in the current space station, and how would they structurally attach to this type of inflatable structure, and how much weight could the Bigelow structures support?
Okay, so initially, you're constrained by the ability of your launch vehicle, right? So in our case, we had to fit within two things: a vehicle that can lift 43,500 pounds, and a vehicle that has a fairing length, of which there is only one at the moment, and for the next foreseeable few years, and that happens to be the Atlas 552 stretch fairing. And so those are the two constraints that we really have in this architecture. So once you are on orbit, essentially you have a tremendous volume to continue to bring up an enormous amount of supplies. These as testing stations also would be ideal, because you could run concurrently two different systems at the same time and be able to validate one or the other, and one may be a system that is older, more reliable because you've had history on that. One might be brand new, you intend to use for deep space, but you don't want to test it out in deep space. You want to test it closer to home. So you could outfit these, and we have about 28 or 30 different design reference missions. Everything from a farm that we heard about earlier today, or a hospital, a medical facility, a surgery area. There are 28 or 30 different kinds of discrete uses that you can put these systems to.
Of Bigelow, it really is exactly that. At an experimental stage, we are yet to see how it would incorporate an actual space station within the two structures attached.
Correct. We are in the early phase of a new kind of spacecraft that offers a lot of promise.
Thank you, and I believe we have a final question from Bill Harwood.
CBS, for Mr. Bigelow, this has been a long time coming for you, getting this thing up to station. It's a big deal. What's your emotional state at this point? How are you feeling about this going into a really critical launch for you guys?
I'm really proud of our staff. I am very thankful to NASA to giving us this opportunity. I hope that things go well tomorrow or the next day, whenever the launch occurs. And so we are thinking ahead, as we always do, in the next project. So we're anxious for this project to be launched and for it to be successful, and then we can start working on the next iteration of the next spacecraft.
Thank you all. Thank you, gentlemen. That is all the time we have for today. Thank you for joining us for What's on Board to discuss this exciting science that's heading to station. As a reminder, our next launch is targeted for Friday, April 8th at 4:43 p.m., and we hope you'll tune in to NASA television. Coverage begins at 3:30 p.m. Have a great day.